Assalamu alaikum wa rahmatullahi wa barakatuh. Today we'll be doing the part two of motors and generators. And if you look at this example that we have here, we see that the direct motor, I'll just read for us, a direct current motor can also act as a direct current generation. Have a look at this animation. The coil, the split ring, the brushes, and the magnets are exactly the same as the motor above, but the coil is being turned, and this turning of the coil is what generates your EMF. So if you look in this example, we see that there is no cell, whereas in the previous lesson that we did, in this case, we have a cell. Here is our cell, and the current goes through the wire in the magnetic field, and then the wire is caused to turn. This is the motor. But if you look at the generator, there is no current. What happens is we move the coil in the magnet and we induce an EMF. So this is what we are doing. We are inducing an EMF. We create an induced EMF. Let me just write it down fast. Induced EMF is what we are creating. And how do you have an induced EMF? We require movement and we require a magnet. So when there is a movement of the wire in a magnetic field, an EMF is induced. And if you look at this example, the split ring commutator allows for direct current to be induced. I will just play this animation and we'll see that the voltage is only in the first quadrant. It doesn't go down in the second quadrant. So if I just play this animation, we'll see that that is exactly what happens, that the motor only plays in the first direction. There we have it going. And again, when the coil is closest to the magnet, when it is in line, we get maximum EMF. As you can see here, you get maximum. And when it is horizontal and when the wires are furthest away from the magnet, like in this way it is now, where it is horizontal, we get minimum EMF, as we can see in this case here. All right, going further, in order for us to use the generator, we use Fleming's right-hand motor rule. Fleming's right-hand motor rule. So it's important not to confuse the left hand with the right hand. The left hand is used for to identify the movement of the motor, and the right hand is used to see the direction of the induced EMF. Induced EMF. So this is important. So the right hand is used to find voltage and the left hand is used to see which way the motor turns. Now the other option is we get alternating current. Now if you compare the direct current with the alternating current, if you look at this case here, and if you compare this generator to this generator, we see that there is a significant difference. The difference is in the DC generator, we've got a split ring commutator. And if we look at this case here, we see that our voltage is in two directions. Our voltage is in two directions, and because our voltage is in two directions, we don't have a split ring commutator anymore. We have a slip rings that are replacing the split ring commutator. So here we have slip rings. So the slip rings are responsible for creating alternating current. And we can see this from the graph, nicely done here. If we just replay the graph, if you just play the case again, we'll see that it goes in the negative quadrant, positive quadrant, negative quadrant, and back to normal. So the split ring, the split ring commutator creates direct current, and the slip rings create alternating current. Now another animation that we have here from this website, as you can see here, we have the needle. The needle is alternating. It's going to the left. Voltage is at 0, going to the right, coming back, voltage to 0, going to the left, and it continues left and right, creating alternating current. And if you look at this diagram, we see that we have slip rings, and we are causing the motion. Here is a handle which you are turning, and as you are causing the motion of the wire in the magnetic field, an EMF is induced in the coil. So that is very important. So just to summarize, we see that if you have a motor, let's see what we are given. In a motor, you are given a magnet. In a dynamo or generator, you are also given a magnet. So the magnet is standard. Then we see that in the motor, you are given the movement. Sorry, you're not given the movement, you are given the in the magnet, in the motor, you need to switch the motor on, so you are given the current. And we see that the motor turns, and we have to find which way there is movement. Which way is the movement, or sometimes they say the thrust, or the force on the coil. Sometimes they even say force on the coil. So that is what we have to find. And when we look at a dynamo, we are given the magnet and we are given the movement or the rotation of the coil, and we want to see which way is our induced current or EMF, depending on which way you want to look at it. So this is an important summary of the motor and the generator. And then one more thing, for the motor we use Fleming's left-hand motor rule. And we want to find the thumb. The thumb comes last. And when we work with the generator or the dynamo, we're using Fleming's right-hand dynamo rule. And here we see that if the current comes last, so the second finger is what we are finding. Here's just an example of an application of the induced EMF. Here we have a dynamo where we've got this piece here on the top that's rotating, and as a result it's rotating this piece here, which is the magnet. So there's a movement of the magnet, and we have it's a permanent magnet, and then we've got coils on the outside. So because there is movement of a magnet, we induce an EMF. So this is how a dynamo works. So what happens is we connect this to your bicycle, and the bicycle tire is connected to this piece here on the top, and then it causes rotation. And in this case, the magnet is spinning in fixed coils, and as a result, we get an electrical output. So that is a summary and introduction to how dynamos work. Thanks for listening.